Hi, welcome to the next lecture on Haskell programming. In this lecture, we will look at a very important concept in Haskell and in functional programming in general, higher order functions. Okay, let us begin. As we know, most functions produce a function as a result. You have unary functions f, which is of type maybe int arrow int. You have binary functions g of type int arrow int arrow int, let us say, and this automatically returns a function, because remember in Haskell int arrow int means it's a function that takes an integer as input and produces a function as output. Okay, so g on x will produce a function which can further be applied on y. Okay, and as we know, instead of putting parenthesis here, we could just put int arrow int. But we shouldn't forget the fact that most functions, at least all functions of more than 2 or more arguments, they return a function. Okay, but the nice feature in Haskell is that you can also take functions as arguments. This is not something that is very naturally done in other languages. In older languages like C, etc., you couldn't do this. You could only do it in some roundabout fashion by passing a pass a pointer to functions as arguments. This is the typical case with most languages, that you cannot pass functions as arguments. Now, more modern languages have incorporated more and more functional language features. So, you will find that it is possible to pass some kinds of functions, at least to a limited extent at least. You can pass functions as arguments, and you will find it in most modern languages, Rust, Swift, etc. Can pass functions as arguments. Let me just say limited use case. Limited, in a limited manner, let's say. Okay, but let's come back to Haskell. This feature is very natural in Haskell and all functional languages, right from the earliest functional language, Lisp. Okay, and here is the first example of a higher order function. We are defining this function called apply. Okay, and apply, it just takes 2 arguments. One argument is a function, another argument is a variable, and it applies the function to the variable. So, for instance, apply of +1 1 should give you 2, is nothing but +1 being applied on 1, which is nothing but 2. Apply of square of 5 is nothing but the square function applied on 5, which is 25, and so on and so forth. Okay, and you might wonder what is the use of such a trivial function. We just want to start with the simplest higher order function possible, and this is one of the simplest. Okay, just to learn more about higher order functions, let's try to figure out what the type of apply is. What is its type? Yeah, so apply. So let's try to figure out on our own. Apply fx. So there are 2 arguments. So let's call the argument type, the first argument, let's call it A, the type to be A. The second argument, let's call the type to be B, and then the result, the body, is fx, right? So f itself is a function type because f is being applied to x. Therefore, it better be the case that f is of type B arrow C. In general, C arrow D, but then f is being applied on x and x has type B, so therefore this C is equal to B. Okay, so therefore the conclusion is that f is of type B arrow D. Okay, and it is being applied to x. So what is the value, what is the type of fx? Fx is of type D, because you have a function whose type is B arrow D. you are applying it on a value whose type is B, and therefore f applied on x should have type D. Okay, and apply fx is nothing but fx. So apply fx, the type of this overall this expression apply, the function apply applied on f and x is also D. And recall that A was equal to CROD, which was equal to BROD. Okay, so overall you have apply will have the type BROD, arrow B, arrow D. Okay, so that's the type of apply. It's really doing nothing. It's just sort of identity. So it takes two arguments and it applies f on x. So this should be the type. And if you want, you can actually make it. You can rename the type variables and just call it A arrow B, arrow A, arrow B. That is the type of apply. Yeah. So this reasoning is done here. A generic function f has type A arrow B. Second argument x of apply is also the input to f. So therefore it had better be the case that the second argument of apply has type A. And output of apply fx is the same as f of x. F applied on x should be of type B. So apply fx is also of type B, right? So finally you have this derivation. Okay, so that's apply. Note the important point that one of the arguments is a function and that is reflected in the type. Typically you will have A arrow, B arrow, C arrow, D, and you will do the parenthesization to the right. But here you have something like this, right? This is the fully parenthesized form of it. So one of these, so your general function will have type A arrow, B arrow, C arrow, D. If one of these A, B or C itself is a function type, then it's a higher order function, right? Which means that it takes a function as one of its arguments. Now, strange as this function may seem, we use this quite often. This is the same as the function dollar. Okay, so plus $1 $1 is nothing but our apply of plus 1 1, and we introduced dollar as a means to avoid unnecessary parenthesis. So we said that instead of writing plus 1 applied on 2 times 5 plus 4, we could have just said plus $1 2 times 5 plus 4. That's fine, and it automatically parenthesizes the whole of the right argument. But dollar is something much more basic. So true, it imposes this parenthesization, but it is also just this built-in. It is one of the first examples of a higher order function. It just takes a function and value as arguments and it applies the function on the value. Okay, let's look at more. Let's look at more useful ones which sort of capture very common patterns of programming in Haskell. Here is a function which we looked at already, capitalize, and we said capitalize, the aim of this function is to convert every letter in a string to uppercase, right? And the pattern was this: capitalize of empty string is empty string, capitalize of C followed by C is to upper C followed by capitalize of C's. Okay, so this is the pattern. Here is another function, square a list of integers. You are given a list of integers and you want to produce a list of integers as output. The output should be, each element should be the square of the corresponding element in the input list. So square list of empty list is empty list, square list of x followed by x's is x squared followed by square list of x's. Okay, and in general the pattern is that you want to apply a given function to each member in a list. Okay, and if you want to really abstract this out, you can abstract this out and say that some f, no matter what f is, could be capitalized or square list or whatever, f of empty list is empty list, f of x followed by x's is given an EF, I want to find a primed version f prime. F prime will apply f to every element in the list. Okay, so we can think of it that we can think of it as that. But rather than take each f and then prime it, there is a much better way of doing it, which is to use a higher order function. This higher order function is called map. It's a very important function. Map is of type a arrow b, which is the function argument, arrow list a, which is the list of elements, each of which is of type A, and then you produce a list of elements, each of which is of type B, which is the output elements. Essentially, map will take a function f and a list x0, x1, xk, and it will produce the output list f x0, f applied on x1, f applied on xk. Okay, this is a simple pattern that we want to achieve, and it is wrong to, I mean, it is not technically wrong, but it is not the correct thought process to use a primitive recursion form instead of primitive recursion form or pattern matching recursion instead of actually using map. Okay, because then using map f, this thing reveals what is happening better. Right? Otherwise, you would have to read each line of your recursive definition and then figure out that, oh, all that is happening is that some function is being applied to every element of the list, right? Because recursion is the most general form. I mean, some kind of computation which cannot fit into any standard pattern that can be expressed using a primitive recursive pattern matching like this. But wherever there is a very well established pattern that you are following, you should use some of these higher order functions that Haskell allows you, and map is one of the most important functions. Here are more examples. I can say map +3 on 2, 6, 8, and that will give me the list 5, 9, 11. Or I can say map *2 on the list 2, 6, 8, that will give me 4, 12, 16. Or I could say map raising to the power 2 on 1, 2, 3, 4, and that would be the same as squaring, 1, 4, 9, 16, etc. Okay. So these are some map examples. We could, the earlier example corresponds to map is the same as square list of L. The code that we wrote as 2 lines of pattern matching recursion, that is nothing but map raised to the power 2 L. Or the capital A's example was nothing but map capital A is L is nothing but map 2 upper L. And recall that whenever you have an expression of the form FL equals or Fx equals Ex, where f is a function name, E is an expression, X does not occur in E. Then it is wasteful to say f of x equals E of x. It is much better to say f equals E. Okay. For instance, here capital I is nothing but map 2 upper. You are describing what that function means. To describe what that function means, you don't always need to specify what that function does on a particular argument. You don't need to name the argument. It suffices to say that capital I is just mapping 2 upper, or square list is nothing but mapping the square raised to the power 2 operation. Okay. So you don't need to mention the list always. So therefore, we would prefer to write it this way: capital I is equals map 2 upper, square list equals map square, etc. Okay, so here is another example. Given a list of lists, I want to sum the lengths of the inner lists. The standard recursion way of doing it would be to say that sum length of empty list is 0 because there is no inner list. Sum length of x colon x's is, or rather L colon L's is length of L plus sum length of L's. Okay, so this is what we want to do. This is what we would do with normal recursion. But of course, you can do this, right? Sum length of L is nothing but sum of map length L. Okay, sum is a built-in function, or rather standard library function. Right, sum of x1 dot 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 xk is nothing but x1 plus dot 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 plus xk. And you are mapping length of L. So it's better to write else. Okay, you have a list of lists, we'll call it else. You map the length function on else, and then you sum the resulting list. Okay, so this else is of type some list of A, but map length else will be of type list int. Because each list of type list A is being mapped to an integer, right? You are computing its length. Right, here is the description of map. Map, now we said that we will replace the normal recursion by map, but then how do you define map? Map itself is defined by straightforward recursion. So map f empty list is empty list, map f on x colon x's is nothing but f applied on x followed by map f on x's. Okay, so this is the definition. So if I have map f x1, x2, x3, x4, yeah, recall that this is nothing but x1 colon x2 colon x3 colon. So map applied on that would be f on x1 followed by map f of which is nothing but f on x1 followed by f on x2 followed by which is nothing but f of x1 followed by f of x2 followed by f of x3 followed by map f of map f on the list x4 followed by empty list, and this is nothing but f of x1 followed by f of x2 followed by f of x3 followed by f of x4 followed by map f empty list, but that is nothing but empty list. So finally I will get f of x1 followed by f of x2 followed by f of x3, right, or in other words this list. Okay, so this is how this function is computed. What is the type of map? I said this already. F is a function that takes inputs of type A and produces outputs of type B, and your inputs should be elements of the list. So the input list is list A, and the output are the outputs of F. So that is list B. Okay. So that's about the type of map. Okay, so map is one function. Map takes map F this is one pattern to remember. This is one standard thing you might want to do. Given a list, I might want to apply one particular operation on every element of the list. Okay, what's another thing you can do? Given a list, I might want to pick out some elements of the list, okay, based on a condition, and this is another common pattern. Let's look at some concrete examples first. All evens, what I want to do is I want to select all even numbers from a list. So I have a list int which is input and list int is the output. All evens of empty list is empty list. All evens of x followed by x's. If x is even, then x followed by all evens of x's. Otherwise, just all evens of x's. So you want to make a decision about whether to keep x in your final list or not. If the predicate even is true on x, you keep x, otherwise you drop x. Okay. So this is the standard pattern. So for instance, all evens of, you can work it out, 1 dot dot 10 or 0 dot dot 9, let's say, should produce 0, 2, 4, 6, 8. Okay, you can try to simulate this and figure out the computation. So the abstract pattern is what is called filter, and filter, I said it takes a predicate even in this case. What is the type of even? The type of even is int arrow bool. Yeah, so even of 4 should give you true, even of 5 should give you false, right. So you take a predicate as the first argument. So that's the filter is also a higher order function. A predicate is also a function, right? It's a function from whatever input type to bool. So a arrow bool. Arrow, you are applying this filter function on every element of the list. So you have a list A, a list whose elements are of type A. What is the output? What is the output list? The output list is a sub list of the original list, right? A sub list is just like a subset. You are just picking out some elements of the list based on whether the condition is fulfilled or not, right? So this is the point. So what would be the definition of filter itself? You just follow the all evens definition, and that's the general definition. Filter P on empty list is just empty list. Filter P on x colon x's. If P holds for x, or in other words, if P of x is equal to true, then x followed by filter P x's. Otherwise, you don't retain x, you just drop x and you just do filter P x's. Okay. So this is the point. Now you can say that all evens is nothing but filter even. Okay, filter based on the even predicate. Okay, that's what it means. So we had the list comprehension notation. So some of it can be expressed using filter, some of it can be expressed using map, some using a combination. For instance, if I want to say pick out all x from 0 to 9 such that even x. So that's you can use list comprehension for this, or you could use depending on context, certain things are more succinct and something might be more succinct and something might be more elaborate. Sometimes there might not be much to choose between the two ways of expressing the same idea. You just go by whatever you feel is more aesthetic, okay, or whatever comes more natural to you. Another example, square x such that x comes from is nothing but saying map square right. So you could use list comprehension to express some things that you expressed using map and filter. Sometimes you have a combination of map and filter in list comprehension. I might want to do x squared such that x comes from 0 to 9 and x is even. And this I would say it is map the square function on filter even right. This tells you exactly what is happening. Okay, you first filter out all the even elements in 0 dot dot 9 and then you map the square function on the resultant list. Okay, so that is the example that I am giving here. Now square evens of L is nothing but map the square function on filter even L. Capital A is vowels. That's another thing I could say. I have a string, I want to pick out all the vowels and capitalize them and then just print them out. So capitalized vowels is nothing but So to express it properly, I would say cap vowels of a string is equal to map to upper filter is vowel of the string, right? But sometimes it is cumbersome to write it in this form, f applied on g applied on x. In high school mathematics also you would have seen this notation f dot g to mean this very same thing. F dot g is the function h such that h of x is f of g of x. Okay. So in Haskell also you have the dot operator. The dot operator, if you think of it as an operator, is of so your right hand side function takes a to b, the left hand side operator, this thing takes b to c, and overall you have a function from a to c, right? That's what composition does. So b to c arrow a to b arrow a to c. Right, but to return to this cap vowels function, I am just filtering using the predicate is vowel, and is vowel of C is nothing but checking whether C is an element of A, E, I, O, U. Recall that element is just checking whether a member, whether an element, whether a value is an element of a list or not. Right, so the dot here in this example denotes function decomposition. F dot G applied on any E is nothing but F applied on G applied on E. Yeah, and as I mentioned, its type is B arrow C arrow A arrow B arrow A arrow C. Okay, so we have so far seen map and filter. There are lots of higher order functions. Let's see some of the more important ones, some representative ones. Take while. This is another function. So take NL returns the n element prefix of L, so which we saw in the previous lecture. Take 5 0.9 is just 0 1 2 3 4. What we want to do is take while. So the same thing could have been expressed as take while so this should give an idea of what take while does. Take while takes a predicate and a list, and it will produce the prefix of the list, the longest prefix of the list which satisfies the predicate. Right? It is the longest prefix of L such that for every x in the prefix, P of x is true. So that is what take while PL will do. So take while of greater than 7, 8, 1, 9, 10 will be just 8, because the moment you reach 1, it fails to satisfy greater than 7. Okay, 1 is not greater than 7. Take while less than 10, 8 is less than 10, 1 is less than 10, 9 is less than 10, but 10 is not less than 10. So that will be 8, 1, 9, right. So in the earlier example, of course, it would be silly to use take while less than 5 of 0.9 instead of saying take 5 0.9. But in general, you don't know how many elements, how large a prefix will satisfy your predicate. Your predicate could be complex, your list could be the result of some other computation, and yeah, so take while is what you want to do then. So for instance, suppose I have a way of generating a long list of primes. We will later see that you can actually generate the list of all primes, which is an infinite list, right. So 2, 3, 5, 7, 11, 13, dot, 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 dot. So now if I might want to list all primes. So let's call this all primes. I might want to list all primes less than 1000. That is nothing but take while less than 1000 all primes. Or I might say list out the first 100 primes, first 1000. Then I would have to say take of 1000 of all primes. So both take and take while have their uses, right? So if you want to extract a fixed number of elements from a long list, then you do take. If you want to extract all elements that satisfy a particular condition, assuming that your list is ordered in some fashion, then this take while less than 1000 is actually giving you all the primes less than 1000. Okay. Okay. Here is another example, position CS, which we programmed earlier, yeah, this was supposed to return the first position in S where C occurs, or length of S if C does not occur in S at all, and that you can say is nothing but length of take while not equal to C of S, right. So for instance, if I have the string, I don't know, let us say my list is the string Arjun Erigaisi, right, and I want to see where G occurs in it, right. So what is take while not equal to G of this is nothing but Arjun space ERIG. What is its length? 5 here plus 5, so 10. Its length is 10. Actually, not G equals this, so it shouldn't even include the G. It should just be Arjun Eri. So length is 9. And what is the position in which G occurs? What is the first position in which G occurs? 0, 1, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, right. So this is the point. So it returns everything before and you have this. So this is just the position and you are returning the first position. Let's say, let's check where I occurs. The first position where I occurs is 9, 10, 11. 11 is where I occurs, and if you do take while not equal to I of the above thing, you will actually get Arjun and then ERIGA, right. You won't include the IS because the moment you see that you have reached a value which is equal to I, you will stop, right. You will not include it. Okay. So this is about take while, and as usual, take while itself can also be programmed using basic recursion. Drop while is the analog of take while. How would you program take while? Let's check. Take while, what is the type of take while that we have given here already? Take while of P of empty list is empty list. P of x colon xs, in case Px holds, then this is x followed by take while Pxs. Otherwise, this is the important case. Otherwise, it is just empty list. Okay. Note the difference between this definition and the definition of filter. For filter, you would say filter P x colon x's, in case P x, then you will say x followed by filter P x's, otherwise filter P x's, right? This is the big difference. Filter will go through the entire list and pick out all elements that satisfy a predicate. Take while will keep on picking out elements that satisfy the predicate. The moment an element fails to satisfy P, it will stop. Okay. So this is an important distinction to remember. In fact, even in this example, take while greater than 7, 8, 1, 9, 10 is just 8, whereas filter of the same thing will be 8, 9, 10. The one does not satisfy the predicate greater than 7, but it's okay. It will skip it and go past and process the rest of the list, whereas take while will stop immediately. Okay. So this is something that one needs to remember. Drop while is the analog of drop. You give a condition and you just say drop while whatever. And as usual, you will have take while P L plus plus drop while P L equals L. Okay. So here is another very nice higher order function called zip. Okay, it's really like a zip, like a bag with two one side and another this thing, and to zip it up means to just to connect this with the this with this, etc. Right. So to connect the elements that are aligned against each other. So that is what you mean by zip. How do you connect? You just form pairs. Okay. So for instance, I might give input I might have one list which is of the form 1, 2, 3, 4. I might have another list which is A, B, C, D. Then from this I can form 1, A. Yeah, the list of pairs by pairing up the corresponding elements. And the definition is just this: zip empty list of the nice thing about zip or the significant thing about zip is that if one of the lists is of longer length, then you will just cut off till the point you reach the end of one list. Okay, so if instead of A, B, C, D, I had A, B, C, D, E, F, G, I would still get 1A, 2B, 3C and 4D, right, because the first list has ended, so you will stop processing. So if the first list is empty, then no matter what the second list is, you produce the empty list. The second list is empty, no matter what the first list is, you produce the empty list. Otherwise, you pair up X and Y and then you zip X's Y's. Okay, that's it. It's a nice function. What is the type of zip? List A arrow, list B arrow, list of pairs AB. Okay, that is this thing. Typically, you will see zip used in, for instance, the same position. How do I have that as an example next? The same position CS, I could have done okay, we'll see examples of where zip is used. It's there is one common use case for it, which is that sometimes you have a list of elements and you want to attach the index of the element along with the element itself. So instead of this, I want 0A, 1B, 2C, etc. So, to do this, you just say zip 0 dot dot length L minus 1 . Okay, so you are zipping the list 0 dot dot till some length L minus 1 along with L, and actually it need not just be length L minus 1, it could be anything larger than length L minus 1 also. In fact, we will see later that you could just specify it as 0 dot dot . 0 dot dot represents the infinite list starting from 0. Okay, we will talk about infinite lists 3-4 lectures down the line. But you can do this, and this is a very common use case for zip. Even more useful than zip is zip width, because zip width will take two lists like this and it will combine them with some function, the corresponding elements, right. So, the function is of type A or B or C. The first list is list A, the second list is of type list B, and then what you produce is a list of elements of type C. How do you produce it? Zip width of F empty list, anything is empty list. Zip width F of anything empty list is empty list. This is the same logic as with zip. Zip width F x colon x is y colon y is instead of forming the pair x comma y, you actually do F applied on x comma y, x and y. Okay, and then you again do zip width F x as y. Okay. For instance, zip width would actually be you multiplication, let us say, you would multiply the corresponding elements. This would be 1 times 3 which is 3, 2 times 4 which is 8, 3 times 5 which is 15, 4 times 6 which is 24, 5 times 7 which is 35. Okay, you would get this list. Okay, so you can do this, right. This is zip width. Okay, so far we have seen map, filter, take while, drop while, zip width. Okay, what more can you do? Yeah, here is a simpler example. Zip width of plus 0, 2, 4, 6, 8 and 1, 3, 5, 7 is 1, 5, 9, 13. Okay, so you're just adding 0 with 1. Okay, you do that.